Okay, so more about bases for vector spaces. Let's consider a basis for R2 will be this set B consisting of the vectors, say 1, -1, and -3, 2. Okay. Now, this is in fact a basis for R2. It's to say, by definition, the span of B. The span of B is R2, and the vectors in B are linearly independent. That's linearly independent. Okay, so now then, what we want to do is give this basis then an order of a sort. A set with two objects in it, like these two vectors, does not have an order. You could interchange the order of these elements and it would be considered the same set B, right? So order doesn't matter for a set, but for what we're going to be doing here, we actually care about an order. To give B an order, we'll let V1 be the vector 1, -1, and V2 will be the other vector, -3, 2. The 1 here for V1 indicates that this vector 1, -1 will be first, and then the 2 here in the symbol V sub 2 indicates that this vector -3, 2 is second in the ordering for B. So B has V1 and V2. Like this. We use parentheses here to indicate that this is an ordered pair, right? Just like in algebra where you would write x comma y for an ordered pair, where it's not just a pair with the value x and the value y, but specifically the x comes before the y in an ordering. That's what the parentheses denote there in basic algebra, and the parentheses here perform the same function. So don't use the braces, use the parentheses, and then indicate the vectors in the order that you like. There's actually something that a basis is great for. The reason why we're even talking about a basis for any vector space is because, first of all, because the basis is some set that spans the space. So here B spans R2. The span of B is equal to R2, that is to say. Well, that means then, of course, that every vector in R2 is expressible as at least some kind of a linear combination of the elements of B. So I think it's clear why we would care about the span of B equaling all of R2. That means everything in R2 is expressible as linear combinations of the elements of B. But why linear independent? Why do we care about that? Because it turns out that if the vectors in your spanning set are linearly independent, then each element in the vector space in question is expressible as a linear combination of the elements of the set, in this case B, and it's unique. There's only one way to do it. So I'm just going to demonstrate that here with this example. So B is V1, V2. Express, say, the vector x. Let's say x has components xy. Express the vector x as a linear combination of the basis vectors v1 and v2. Okay. So find okay, I'm looking for letters here. So find A and B. No, let's use C1 and C2. Find C1 and C2 so that or such that C1 V1 plus C2 V2 is equal to X. So X would be a linear combination of V1 and V2. Right. As with a lot of things in this class, it all comes down to being a system. That's C1 and 1, negative 1 there. C2, negative 3, 2 is equal to xy. I think I'll actually make one change here, a very minor one. The components for the vector x, I think I'll call x1, x2 instead of xy, just because. I don't think that changed anything else here. Right. So here we write x is x1, x2. Okay, so we got a system C1 minus C3 minus 3 times C2, that is, equals x1, and negative C1 plus 2C2 is equal to x2. That's a system. Now, if you add these equations, you get negative C2 is x1 plus x2, so C2 is negative x1 minus x2. Then we go ahead and put that into, say, this equation. Here you see that C1 is 3 C2 plus x1, and the C2 we substitute in, probably should point to that there. So we have C1 is all this good stuff here. Negative 3x1 gives a negative 2x1 minus 3x2. Okay, so that's C1. So then, our C1 given by this and our C2 given by this are the scalars, the coefficients of V1 and V2 that we need in order to get the combination of this linear combination of V1 and V2 to equal the vector x. So I'll put that together here. C1, V1, where C1 is this, that's negative 2x1 minus 3x2 times V1 plus C2, V2. C2 being this, negative x1 minus x2 V2. Okay, well that equals our vector x, which is x1, x2. Now it turns out that this is the only way. These values for C1 and C2 are unique. They're the only choices that we have to put here and here, specifically these values, so that this linear combination of V1 and V2 equals the vector x that we have here, which is just an arbitrary element of R2. There's no other choice. Any element of R2 has a corresponding linear combination of V1 and V2 which equals that element, okay? Because this is generic. This vector x in R2 has components x1 and x2. x1 and x2 are any real numbers of your choice, right? So this is basically representative of any element of R2 you like, and we did indeed find values for C1 and C2, namely these values, so that this linear combination of V1 and V2 will equal x. But it's the only choice, so there's nothing else. Okay, when we did the math here, we didn't find other ways to express C1 or C2 that would work. So in fact, we call these values for C1 and C2 that we got here the coordinates of the vector x with respect to the basis b. So we call these guys the C1, which is negative 2x1 minus 3x2, and the C2, which is this here, negative x1 minus x2. We call them well, I use the term, as many books do, the b coordinates. Of the vector x. I believe that the textbook you're using for this course says something like the coordinates of x with respect to v1 and v2 or something like that. So for instance, okay, so I need some real estate here. What we don't need anymore is this stuff that we used to find C1 and C2. Get rid of that. We write as follows. The b coordinates of x symbolically can be written like that. X surrounded by square brackets with the little subscript b there indicating our basis for R2. Now that's to say, well, x is, of course, this. So we could also write that, of course. So we write this or this to denote the b coordinates of x. Here we have the b coordinates of an arbitrary element of R2 with components x1 and x2 is equal to C1, which is this, and C2, which is this. Okay, now again, you can use either one of these symbols here, so I'm just as apt to use the smaller symbol because less writing, so I think I'll actually just stick that in there now. Either way is fine though. So those are the b coordinates of an element of R2. So now I need a definition. We should just give a general definition here. I think I can start erasing some stuff up here. If b equals x v1, v2, vn is an ordered basis for a vector space V, now, the basis B has these n vectors in it, labeled v1 through vn, and this is the order. v1 first, v2 second, up to vn last. That makes sense, right? The 1, the 2, the up to n. So the ordering is just simply given by the subscripts of the symbols, 1, 2, 3, etc. So if it's this is an ordered basis for a vector space V, and let me use like W or something is an element of the vector space V. No, I'll do it like the textbooks. A little v. This vector V is in the vector space big V. Then the b coordinates of the vector V are as follows. B coordinates of the vector V are the numbers C1, C2, down to Cn. If C1, V1 plus C2, V2 plus up to Cn, Vn is equal to V. This is by definition. So the b coordinates of the vector V, denoted by this symbol, is this list of numbers C1 down to Cn if the C1 times the V1 plus the C2 times the V2 plus dot 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 Cn times the Vn, if that linear combination of the basis vectors V1 through Vn is equal to the vector V. So I think you see maybe why we need the order for our basis. If we didn't have an order for the basis, then we wouldn't have this. We would be able to move these around, right? And then we'd go crazy because we wouldn't really have a good coordinate system to work with. So C1 is understood to be the coefficient of V1 by virtue of the fact that C1 is first in this n by 1 matrix. It's the top entry. And then C2, being the second entry, is understood to be the coefficient of the second vector in the basis B, namely V2, like that, C2 times V2, for the next term in the linear combination. And so on down to Cn is understood to be the coefficient then of the last vector in the basis B, which of course is Vn, giving us the last term in the linear combination that adds up to equal V. Okay. Now generally any vector space will have usually different possible bases. And even for a given basis such as this one, you can put them in different orders, right? We could decide to call, V2 the first element in the basis, maybe call it U1, and then let V1 be called U2. And then maybe all the others are the same. So just change the order of the first two guys. That would be considered a different basis, really, because you took a different ordering of the same vectors. And correspondingly, the coordinates for various vectors in your vector space would change. Change the order in the basis, you're going to change the order of the coordinates. Yeah. Theorem here. The B coordinates of a vector V in a vector space, big V, are unique. That's kind of crucial because whenever you have a coordinate system, you would like it to be that every place on the map has a unique set of coordinates. If that's not the case, things start to get confusing. So you want to have it so that when you say that a vector V has coordinates 1, 2, then that's the only possible coordinates it could have, and it can't also have coordinates -3, 7, because effectively that would mean that V is existing in two places, and you really don't know which place is actually the right place. Well, really it would mean that both places are right, and you got a maddening coordinate system that doesn't really work well, because you can't uniquely locate things. You prove this. Suppose the B coordinates of V are A1 to AN, and also the B coordinates of V could be given as, say, B1 to Bn. So in other words, A1 to An are B coordinates for V, and also B1 to Bn are B coordinates for V. In other words, then, bearing in mind that this kind of a thing here you could write as the sum, as k goes from 1 to n, of C sub k, V sub k, a real space-saving notation, so we'll use that here. If A1 through An are B coordinates for V, then that means what we're saying is that the sum k going from 1 to n of AK Vk is equal to V, and B1 to Bn are B coordinates of V, so that means that the linear combination of the basis vectors V1 to Vn with coefficients B1 to Bn, okay, so that's our Bk as k goes from 1 to n, also equals V. Okay, so in other words, we're saying that we've got this linear combination of the basis vectors V1 to Vn equaling the vector V, and also this other linear combination of the basis vectors is equal to the vector V. Now what you can do is this, you say, okay, so sum k going from 1 to n of AK minus, of AK times Vk minus the sum as k goes from 1 to n of Bk Vk, this minus that is equal to this, that's V, minus that, also V. Right, so in other words, I'm just subtracting this equation from that equation. Well, V minus V is the zero vector, so we know that. So this is equal to the zero vector. Okay, so let's see where that takes us. We can combine these sums. This is the sum as k goes from 1 to n of AKV minus BKV. Ooh, something funny going on? No, it's fine, okay. So, subtract the corresponding terms of the two sums equals zero vector. Okay, so then a little bit more buff and polish here. Sum k going from 1 to n of, we can certainly factor out the vk here. So now we got AK minus BK times VK in there equals the zero vector. Now, the thing is that VK, the VK vectors, k going from 1 to n, they're your basis vectors. Okay, it's a basis. That means that these vectors v1 to vn are linearly independent. That means that if you set a linear combination of these vectors equal to the zero vector, the only way that that can work is if the coefficients of the vectors are all equal to 0. So v1 to vn are linearly independent by virtue of them being elements of your basis. So this equation here, this can only be satisfied if all of these scalars, each of these scalars in front of our vectors vk here, are equal to 0. So AK minus BK must equal 0 for each k from 1 to n. That is AK equals BK for all k. A1 must equal B1, all the way down to AN must equal BN. So these B coordinates for V, they're the same. Where to put that? Okay, let me get cleaned up. So, A1 to AN is equal to B1 to BN. So, if you posit that a vector in your vector space has two different sets of B coordinates, you find that in fact, well, if you say it has these B coordinates A1 to AN and these B coordinates B1 to BN, you find in fact that all of these values here are equal to those values over there, right? They're actually the same set of B coordinates. So the vector V has unique B coordinates. Now just bear in mind that when you write something like this, what you're saying is, here, writing this, means that this linear combination of the basis vectors V1 to Vn is equal to the vector V. And when you write this, you're saying that this linear combination of the basis vectors is equal to the vector V. And it is not an immediate thing that this linear combination and this linear combination have exactly the same coefficients. The AKs here and the BKs here are not, at least on the surface, seen to be the same. You have to do a little argument here, which is what we did, using linear independence to finally argue that in fact the AKs and BKs are all the same. So you don't get to say, well, this matrix equals this symbol, and this matrix equals the same symbol, therefore this matrix must equal that matrix. Of course, in the end, that's how it turned out, but you can't argue the proof that way. When you write this and you write this, you're saying really this, and these do not necessarily scream out that the AK is equal to BKs right away. Okay, so that's just a little tip about, well, what the notation is doing for you by way of convenience, but don't go too crazy with it. Don't use the notation to try to prove things that aren't actually trivial. So then, that is the first bit here I wanted to talk about. Okay, rock and roll. More good stuff. Some things here on the board. We get into the idea of the dimension of a vector space. A vector space V is finite dimensional if it has a finite basis, which is to say it has a basis which has a finite number of vectors in it. Otherwise, you would say that V is infinite dimensional. One thing this kind of glosses over is the idea of, well, what if you have a vector space that doesn't have a basis? But as a matter of fact, every vector space does have a basis of some kind. That's actually proven in the notes in section 3.6. Although it is somewhat technical, it does use some concepts that are not actually developed in the notes. They're a little bit but it doesn't require calculus or anything that fancy. But just take it as a given that any vector space has a basis. And if you have a vector space and you can find a basis for that vector space that only has a finite number of objects in it, a finite number of vectors, then it is finite dimensional. Most of the vector spaces that we deal with in this class will be finite dimensional, though we do occasionally look at certain things that aren't. Here's a theorem. Any two bases for a finite dimensional vector space V contains the same number of vectors. So if you find a basis for a vector space and it has 8 things in it, and then you find some other vectors, another basis for that same vector space, you can be sure that that will also have 8 things in it, no more, no less. That's really nice. So to develop this idea a little further, first some notation. If S is a set, in general, then putting bars around the S, this denotes then the number of elements in the set S. So if S contains the elements -2, 0, and 18, then the number of elements in S is 3. The idea of the number of elements of a set is also known as the cardinality of the set. Another word that's used in the notes especially. If you've got this set B that contains V1 through Vn, of course we might think of this possibly as some basis for a vector space, then the number of elements in B is clearly n. Okay. But with this theorem, which tells you that for a finite dimensional vector space, again, any two bases has the same number of vectors, you can meaningfully define what's called the dimension of the vector space. The thing is that if V has a basis B1 and the number of elements in B1 is n, and B2 is another basis for V, then the number of elements in B2 is likewise n. So we can meaningfully define the dimension of a finite dimensional vector space V, which we'll denote by dim V, as being equal to the number of elements in any one of its bases. And it doesn't matter which basis that is. You are kind of in the way. Alright. So, if B is a basis for V and the number of vectors in B is n, you would say that the dimension of the vector space V is equal to n. Or you have an n-dimensional vector space. A basis for R3, for instance, contains these 3 vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. And so the dimension of R3 is, guess what? It's 3, and that's good. In general, the dimension of Rn is n, as you can easily show. Okay, so that gets some of the terminology and notation and such, and the basic theorem here out of the way. And we want to look at an example here of finding the dimension of a given vector space. Let V be the solution set to the matrix equation AX equals 0. Matrix A will be this 4x5 matrix, as you see. This would mean that the vector x here would actually need to be a vector in R5, because with a 4x5 matrix, you have to multiply it with a 5 by something matrix, and x therefore must be 5 by 1. So then that would be then the 5 by 1 0 vector, 5 zeros in a column. And we'll do 2 things. We'll show that V is a subspace of R5, and part B, then find the dimension of V as well. What I have here is the start of finding B. But for part A, I want to point out that it's already been done in a lecture, I think, but maybe not. It's in a homework assignment. Pretty sure of that. But this you could just say more generally. The solution set to any homogeneous system of equations is a vector space in its own right, hence a subspace of whatever larger vector space might happen to contain it. So, I guess I should put that in writing now. The solution set to any homogeneous system of equations is a subspace. And all you got to do is just note that, well, a homogeneous system can always be put in terms of a matrix equation like that with the zero vector on the right-hand side, right? So what we're really just saying then is that the solution set to a matrix equation such as this with the zero vector on the right must be in fact a subspace. And just a quick sketch of how you would show that, and then we'll get on to part B here. Suppose the vectors, well, let's use, yeah, sure, vector x1 and vector x2 are solutions to ax equals 0. And again, we're using a matrix equation to represent our system of equations. Then, what does that mean? That means that ax1, a times x1 is 0, and a times x2 is 0. Now what you find is that a times x1 plus x2, which we know from the properties of matrix multiplication and things like that developed in chapter 2 of the notes or the text, that, well, this is ax1 plus ax2, right? So that distributes in. And now ax1 is 0, ax2 is 0, so this is 0 plus 0, and therefore we get the 0 vector. And hence, x1 plus x2 is a solution. So if x1 and x2 are in the solution set to this homogeneous system, this here, you find that x1 plus x2 is likewise a solution and belongs therefore to the solution set to the system. So in other words, the solution set to the system is closed under vector addition. All you have to do is then show in a similar way that it's closed under scalar multiplication, and you have the two closure properties nailed down, and the last thing you formally have to do to make the case that the solution set to the system is a subspace is just to make sure that it's not the empty set. A subspace, to be a subspace, must, for instance, at least contain the 0 vector. But that's easy. If you let x be the 0 vector, clearly a times the 0 vector will equal the 0 vector. So the 0 vector is in the solution set to the system. So it's not empty. It's not the empty set. The solution set is not empty. So all of that kind of stuff would tell you then that, okay, yeah, the solution set to any homogeneous system is a subspace. And so part A, you pretty much just have to say that. V is a subspace of R5 in this particular example, simply because this particular example is just an example of this more general situation. So that's taken care of. So I mean, to show that this is closed under scalar multiplication is easy. Take one of your solutions here, x1, and just show that c times x1 is also a solution. A times c x1 is equal to c times a x1 is equal to c times the 0 vector is equal to the 0 vector. So this shows you then that c times x1 is also a solution. So we have closure under scalar multiplication. So that's pretty much it. There. Now it's totally done. So we can get on with this part B, find the dimension of this particular solution set V to this particular matrix equation AX equals 0, where A is this 4 by 5 matrix. Start off, we're going to use Gaussian elimination. Let's do some urban renewal over here. Okay, now you want to get this into a row echelon form in the manner of chapter 2. So really you should be getting pretty good at this by now. Do -2 times row 1 added to row 2 to get a new row 2. Do -1 times row 1 added to row 3. And -2 times row 1 added to row 4 to get zeros here, here, and here. You want these to be zeros. So -2 times row 1 plus row 2 to get a new row 2. Get a 0. That's a -2 times 2 is -4. Added to -1, get the -5. Here you're going to get a -2. A 1 stays there. And that gives you a 2 plus 3 is a 5. Now this is a homogeneous system, meaning there's a 0 vector on the right-hand side rather than something that's not the 0 vector. So all you have over here is zeros. So usually when you do the Gaussian elimination and you write the so-called augmented matrix for the system, which is what this is here, you can safely just lose this last column because it's always going to be 0 every step of the way. So it's understood that there's a column of zeros at the end here, but we will no longer write it. Okay, so -1 times row 1 added to row 3. Here we go, we get a 0 there, -5, -2, that stays a 1, and we get here a 5. Interestingly, these two rows here are the same now. That's nice. Okay, we'll see how that takes us. -2 times row 1 added to row 4, getting a new row 4. You get your 0 here. Here you get a -4 plus 9 is 5. -2 plus 4 is 2. That remains a -1 there. And then here you get a 2 plus -7 is -5. Of course, this last row is just the opposite of the form of the second and third rows. We can add the negative of row 2 to row 3 to get a new row 3. And then just add row 2 to row 4 to get a new row 4. In so doing, these last two rows just become all zeros. Okay, So, are we there yet? Yeah, we have a row echelon form. The first non-zero entry of row 1 has nothing but zeros under it. The first non-zero entry of row 2 has nothing but zeros under it. And then after that, we've just got rows 3 and 4 are all zeros. So this is a row echelon form. Now what do we do? So you could get this thing even further reduced using Gauss-Jordan elimination, where you then work to get a 0 above this -5, for instance. It's really probably not worth it. At this point, we've got the system beaten down to a fairly minimalist form. So we gotta just pick a pin here that isn't dried out, and write out what we really have now. Teleport this over here. What we have is x1 plus 2x2 plus x3 minus x5 is equal to 0. Don't forget that there's really just a bunch of zeros in this last column here. So equals 0. So we have that. And the second row gives us -5 x2 minus 2x3 plus x4 plus 5x5 is 0. That is our system at this point. Now what do? Well, get one of these variables in terms of the others. There's some low-hanging fruit, like here, x5 is, this one shows us that x5 is just equal to x1 plus 2x2 plus x3. Okay, and then you can put that in there. And then we get something new and wonderful for that equation. So 5x5. 5x5 is 5, x1 plus 10x2 plus 5x3 equal to 0. We really need none of this work down here anymore. Combine some like terms. We have 5x1 plus 5x2. When you put those together, Oliver and Stanley there, and 3x3, and okay, that takes care of them, and then x4. Now then, we have x5 in terms of x1, 2, and 3. We can also get x4 in terms of x1, 2, and 3. There's many ways we can do this. However, this is the way I've gone. So now we have x4 is -5x1 minus 5x2 minus 3x3. That's an equal sign there. That's basically as far as we can go. There's an infinite number of solutions to this system. Solution set, that would be the V here, is the set of vectors with components x1 through x5 such that the x4 and the x5 are given by these equations here. Well, why don't we call this, say, 1, we'll call this 2. So I'll just say it's the vectors with components x1 through x5 such that 1 and 2 hold. Now the object of the game is to figure out the dimension for V. I guess I should make mention that the whole point of finding, in order to find the dimension for V, we need to find a basis for V in this case. There's really no other way. We have to find a basis for V, and any basis for V that we find, all we have to do is see how many vectors are in it, and then that by definition would be the dimension of V. So we're trying to express V in some format where we can then identify a basis. Now up to this point, it's just been a matter of finding the solution set to a system of equations, so it's been more like a chapter 2 type problem. But now we do have to go a little further. We have V is x1, x2, x3. We might need to make that a little bit bigger. x1, x2, x3, and then x4 by equation 2 is given in terms of x1, x2, and x3. It's negative 5x1 minus 5x2 minus 3x3. And then the x5 down there, using equation 1, is x1 plus 2x2 plus x3. That's a 5 by 1 vector there. Such that, well, what do we say after the such that? Well, for lack of anything else, we just simply would specify that x1 and x2 and x3 are real valued. So all vectors of this form, where each of the components, you may notice, are in terms of just x1, x2, and x3, where x1 and x2 and x3 are any real numbers. We're close to being able to figure out a basis for V now. Need a little more room here. So we now, with this stuff, we no longer need this stuff. We could call, let me think here. Yeah, so we'll call x1 S, x2 we'll call T, and x3 we'll call, say, U. Any particular reason? Not really, except that it's done. They are our free parameters, in a manner of speaking. So we can write this now as STU minus 5S minus 5T minus 3U, and then here S plus 2T plus U. I said ST and U are elements of the reals. I suppose the reason why I'm doing it is because textbooks do. And all we're doing is just relabeling x1 and x2 and x3 using slightly less wordy and clunky symbols. But here's the trick. Break this stuff up. The stuff with S in it, stuff with t in it. The terms with t. And then the terms with u. 0, 0, there's a u. Minus 3u plus u. Again, s, t, and u are reals. You could skip a lot of these steps. If you've done a lot of these, you get some experience, and you could just start skipping around. Though I hasten to add that on exams, you should show some, well, make sure that the work is such that I can follow what you're doing. So, a little more to do. The s here, we can factor out of this vector. This is s times 1, 0, 0, negative 5, 1, plus t times 0, 1, 0, negative 5, 2, plus u times 0, 0, 1, negative 3, 1. And once again, s, t, and u are real values. What we have here is linear combinations of these three vectors. Let's see, let's call this guy v1, we'll call this guy v2, v3. So what we have is this is the span of v1, v2, v3. Right? This is the set of all the linear combinations of these three vectors. A basis for V has to be a spanning set that's linearly independent. Okay, well, we just found a spanning set. So if these three vectors are linearly independent, this will be our basis. So we have these vectors v1, v2, v3, and we found that the solution set V to this matrix equation is the span of those three vectors v1, v2, v3. So these vectors in particular, we just need to show that they're linearly independent, and we'll know that this set here is a basis for V. And since it has three elements, three vectors in it, we would then know that V is a three-dimensional vector space, a three-dimensional subspace of R5 in particular. So right now, the only tool we have available to us to figure out that vectors are linearly independent is the basic definition. We set up a linear combination of the three vectors, set it equal to the zero vector, and show that these coefficients, C1, C2, and C3, are all necessarily equal to 0. So we would let this equal 0. Maybe a better word is suppose that's equal to 0. C1 times the V1, which is this vector here. All right, if you look, then we can see that we have C1 times V1, C1 times V1. You get a C1 times 1 here, plus C2 times this guy gives you a 0 up here, plus C3 times V3, another 0. So here we have C1 is equal to 0 right away. be a little more explicit though, I guess. We'll just the zero vector is 0, 0, 0, 0, 0 in this case. C1 times 1 plus C2 times 0 plus C3 times 0 is equal to 0. What does that give us? It gives us C1 equals 0 right off. And then C1 times 0 plus C2 times 1 plus C3 times 0. Oh, so 0. So that's C2 times 1 equals 0. So we get C2 is 0. Okay. Negative C5 times C1 plus negative C5 times C2 plus C3 is equal to 0. Okay, well wait a minute. C1 and C2 are both 0 already. So, putting that there, right, and putting that there, we pretty quickly get that C3 is also 0. So C1 is 0, C2 is 0, C3 is 0. So we found out that that's the only way to have this linear combination of V1, V2, V3 equal 0. So the vectors V1, V2, V3 are linearly independent. Okay, well, the three vectors span V. V is the span of the three vectors. And those vectors are linearly independent. Therefore, this here is a basis for V. Therefore, the set with the vectors V1, V2, V3 is a basis for V. Therefore, the dimension of V is 3. Now that does finish this problem. And I hope to do more, so to be continued. Row and column spaces. We consider the M by N matrix A with these entries. All right. Now, as we've done somewhat in the past in this class, we can label the columns of A as vectors. So the first column of A, C1, you do this all the way down the line. The last column of A, if you watch the indexes, row 1, column 1, all the way down to row 1, column N. So this is the nth column vector of A. Okay. So we call these the column vectors. Of A. The column space of A is, well, first of all, we denote it by COL for column A, is the span of the column vectors. It's as simple as that. Now each column vector of A, if you notice, like C1 has components A11 down to AM1, so C1 and all these other column vectors of A are in fact vectors in Rm. So since the column vector CK is an element of Rm for each, well, call it CJ actually, CJ for each j from 1 to n, the column space of A is a, in this case, is a subspace of Rm. Recall that if you took any collection of vectors in a vector space, such as C1 through Cn here, and take the span of those vectors, what you end up with is a subspace of the vector space. The span of any collection of vectors in a vector space is a subspace of that vector space. This is somewhere proven in the middle of chapter 3 of the notes. It may be proven in the textbook for the course, I just don't know where. So that's just the fallout from that fact. Okay. That nails that down. Now the rows. So the matrix A, we can also label its rows. Row 1 down to row, okay, well you can look and see that you've got the first row all the way down to, that M there indicates the mth row, so it's a row M. So those are the row vectors. Of A. And the row space of A is, first of all, we denote the row space of A by row A, and it is the span. It's the span of the row vectors of A. At least that's what you could say. Fair enough. Although, I like to have the vectors in the row space of A also be vectors formatted as columns, the same as for the column space of A. With this consistent formatting, it's generally easier to do calculations and present theorems and things like that. So it's an easy thing to do. In this case, all we have to do is just take the transposes of these guys. At least this is how I do it in the notes, so I'm going to be consistent in that regard. We'll have R1 transpose to Rm transpose. Okay, so now these are our column vectors, but the row space of A then is the span of the transposes of the row vectors of the matrix A. But now these are column vectors just like these are, and these guys then have, of course, these are in Rm, right? Since Ri transpose is in Rn, for each I from 1 to m. Okay, so the row space of A is a subspace of Rn. R1, for instance, has coordinates A11 through A1n, so it has n components, n coordinates. So R1 transpose likewise has n coordinates So it's an element of Rn. Okay, so this is covered. So here's an interesting thing. There's a theorem in section 3 point, well, toward the end of chapter 3 in the notes. I could look it up, I guess. Anyway, it's the section in the notes that discusses the rank of a matrix. Now, it turns out that, as a fact, it's proven there, that the dimension of the column space of A is always equal to the dimension of the row space of A. Again, recall that the row space of A is a subspace of Rn. The column space of A is a subspace of Rm. So they're each subspaces, but their dimensions are equal. That is interesting. It's not at all obvious. It is again proven in the notes. So this takes care of some of the basic definitions going into this new section here. I will now take a look at an example. Oh, I guess there's a little more notation yet. The dimension of the column space of A is sometimes called the column rank of A, and the dimension of the row space of A could be referred to as the row rank of A. So, since they're always equal, the column rank and the row rank of a matrix A is always the same thing, always the same number, we then just refer to the rank of the matrix. So we define the rank of A to be, well, first of all, the notation we use is rank A, and it's equal to the column rank of A, or the row rank of A. Again, they're equal, so it doesn't matter. So you could just say that the rank of A is the dimension of the column space of A, and that's good enough for us. Okay, so we want to look at an example now. Let A and B be matrices. We say that B is row equivalent to A if B is obtained from A via a succession of elementary row operations. So there are three basic elementary row operations. One, right, adding a scalar multiple of one row to another row, or interchanging two rows, or multiplying a row by a non-zero scalar. And that's it. And so those are the kinds of things you did in order to perform Gaussian elimination to solve a system of equations back in chapter 2. So you should be familiar with the elementary row operations. And a theorem here states that if B is row equivalent to A, then the row space of B equals the row space of A. Okay, and that's actually nice. A consequence of this, in fact, is that the rank of B will equal the rank of A, right? And recall why that would, well, see why that would be is as follows. The rank of B is rank of B is equal to row rank of B, right? The row rank and column rank of a matrix are always the same value, and so that value we just call the rank of that matrix. So if the row, whatever the rank of B is, it's equal to the row rank of B by definition. And that's, of course, just the dimension of the column space of B. Row rank of B is just that. Oh, oops. Dear. I should say row B. A row rank of B is the dimension of the row space of B, of course. Okay, but row space of B is equal to the row space of A. So this would equal the dimension of the row space of A. Okay. That's the row rank of A. Okay, so this is equal to the row rank of A. It's just, of course, the same thing as the rank of A. So rank of B is equal to rank of A. This theorem I'm not proving here. It is proven in the notes. But an immediate consequence of it is this boxed result here, which the proof is, as you see, quite short. Now, there's corresponding results for columns. If we say that B is column equivalent to A, that really should say if. B is obtained from A via succession of elementary column operations. Alrighty. And this theorem has a corresponding, result. If B is column equivalent to A, then the column space of B is equal to the column space of A. So just replace row equivalent with column equivalent, and over here, row B equal row A equal, it becomes column B equals column A. And we still get this result, same thing. Okay. So now we're ready to do, I believe, a real example. I said there was going to be one, and then I remembered, oh yes, we got to do this first. Okay, so let V be the span of the set S, where S contains the four vectors that you see here. You can see that these four vectors are, in fact, in R5. And what we want to do is find a basis for V, pure and simple. And just as an aside, R5 is 5-dimensional, just as we found earlier that R3 is 3-dimensional, meaning any basis for R5 has to have 5 vectors in it. So this set S has only 4 vectors, so certainly this is not a basis for all of R5. It has no chance of being any such thing. Which is not something directly germane to this problem, but, it's just something I'd like to point out. So what we would be seeing here is that V, which is the span of these 4 vectors in R5, is a subspace of R5, but it won't equal R5. You're not going to expect it to equal R5. So a basis for V. This is a basis for V if these 4 vectors are linearly independent. Of course, we could do our usual thing to determine whether these 4 vectors are linearly independent or not. Unfortunately, if we find that the answer is that they're not linearly independent, all that work will be useless in going about then finding a proper basis for V. We'll have to start all over again doing something else. So what we really would like to be able to do is to have a methodology of finding a basis for V that is direct and doesn't have us going off finding out stuff that turns out not to be useful for us. Okay, I mean, again, if we find that these are linearly independent, if this set S is a linearly independent set of vectors, we would be done. This would be our basis. But if we find that they're not linearly independent, where does that leave us? Back to square one, basically. So that's what we're going to do here, is come up with this method. The trick will be to set up a matrix A. Let A equal the matrix whose rows will be made up of the entries of these four vectors. In other words, this vector here, 1, 2, 3, negative 1, 0, that'll be the first row of A. 3, 6, 8, negative 2, 0, that'll be the second row of A. You might ask, does it have to be the second row of A? No, it could be the third row or the fourth row. I'm just simply writing them down in the order they're written here. You could write them in any order, in fact. So then we have our negative 1, negative 1, negative 3, 1, 1 for our third row. And finally, our fourth row. And there we go. So we note that the row space of A is the span of the transposes of these four rows. Here we have row 1, row 2, row 3, row 4. And by definition, the row space of A is the span of the transposes of R1 through R4. Of course, that is R1 transpose right there, right? R1 is this and R1 transpose is that. It's standing up straight. So, R2 transpose, R3 transpose, R4 transpose. So, the span of this set of vectors is precisely the span of this set of vectors. That's S. Span of S. And the span of S is V. So, the row space of A is V. So the job of finding a basis for V is the job of finding a basis for the row space of A. Now here's the object of the game at this point. The object of the game is to find a basis for the row space of A, and that will be easiest if we find a matrix that is row equivalent to A that is in row echelon form. So we would do Gaussian elimination on this, in other words. We find a row equivalent matrix B that is in row echelon form. That is to say, we perform elementary row operations on A until such time as we get a new matrix B that's in row echelon form. And once we get to that point, then we go forward with the next step. But let's just do that first, because actually the bulk of the work is just that. It's pretty mechanical. We take A, and all right, we want to get row echelons formed, so we need zeros below this stair step here, right? In this 4 by 5 matrix. So we need zeros here. Let's do -3 row 1 add to row 2. To get a 0 there, -3 times 1, add to 3, get a 0. Okay, -3 times 2 gives you -6, add to this 6, get a 0 again. That's not something we require, but it just happened to come out. -3 times 3, add to 8, get -1. Here you get a 1, that stays 0. Alright, good, good, good. Now we do row 1, add to row 3. That'll give us a new row 3. 1 plus -1 is 0. 1, 0, 0, 1. Finally, we do 2 times row 1, add to row 4 to get a 0 here. So there we are, 0, and 4 plus -3 is 1. 6 take away 5 is 1. -2 plus 1 is -1. That stays 1. Awesome. We now have zeros here, here, and here. We need these to be zeros. Okay, so we have a little problem, of course, because in order to get that, we needed a non-zero number here, right, in order to kill off these ones and get them to be zeros. So we don't have that. We're going to have to interchange some rows, like interchange. And remember, we want to do row equivalents. We're aiming for row equivalents, so you can only do row operations. So you can interchange what would look best. I think it would be best to interchange 2 and 4. I don't think it makes much of a difference, so just R2 will change with R4, interchange with R4. So, the bottom row is here now. 0, 1, 1, -1, 1. Third row stays where it is. And then second row is down here at the bottom. 0, 0, -1, 1, 0. Beautiful. Okay. Now Q can get a 0 here. So I'm going to go a little cheap here. Because this is a video, we can get away with this. At least I can. I'm just going to take -1 times row 2 and add it to row 3 to get this 0 here that we want. And then, make the appropriate changes down the line. And I'm just going to do that on the spot. Negative of R2, add to R3 to get a new R3. That keeps this 0. This -1 adds to 1 gives you a 0. So this would become a 0. And then -1 add to 0 gives you a -1. That becomes a 1 there. And then that's a 0. All right. Now we just need a 0 here. And that's easy. All we have to do is the negative of row 3 added to row 4, right? So in the blue, what I did there is I took negative of row 2 and added it to row 3. Now I'm going to do row 3 added to row 4, add to row 4. Oops, negative row 3, add to row 4, right? We need that. So we get a 0 here and a 0 here. Now this has the appropriate row echelon form. Zeros under the staircase. It is a beautiful thing to behold. Now we're ready for the next step. We'll call this matrix B. Call B. We can get rid of some of this here. So B is row equivalent to A. By the theorem that I gave earlier, okay, the row space of B is equal to the row space of A. So far, so good. So, since the row space of A is equal to V, we have that the row space, well, I should probably write it this way, V is equal to the row space of B. The row space of B, of course, is the span of the row vectors of B. One should say maybe, well, one of the row vectors of B is the 0 vector, which could be just thrown out because the 0 vector contributes nothing to the span. The span of any collection of vectors would include the 0 vector because one of the linear combinations of any bunch of vectors that you happen to have on hand would be to add 0 times, well, to do the linear combination in which the scalar in front of every vector is the number 0. So the 0 vector is in any span of vectors. So really that 0 on the bottom row there, that 0 vector is not needed. Okay, but here's the key thing. These 3 row vectors of B are in fact linearly independent. These numbers here are called the pivots of B. The pivots of a matrix like B is the first non-zero entry in each row. So for the first row, the first non-zero entry is the 1 here, so that's the pivot. The second row, the first non-zero entry is this 1 here, so that's the pivot. Third row, you have to go in a little deeper and get to this -1, which is non-zero, and that's your pivot for the third row. And then there's no pivot for the fourth row. When you get a matrix into row echelon form, the row vectors of the matrix, the non-zero row vectors of the matrix are linearly independent. This is a fact. The row space of B is the span of the transposes of the row vectors of B. So that's the span of 1, 2, 3, negative 1, 0, 0, 1, 1, negative 1, 1, and 0, 0, negative 1, 1, 0. So those are your three row vectors of B, and the row space of B is the span of the transposes of the row vectors. And you can check easily that these are in fact linearly independent, but you already know this from what I just said. Once you get a matrix in a row echelon form, the non-zero row vectors, the row vectors of the row echelon form matrix that are not the zero vector, so that would be here the first three rows, they're linearly independent. And if you take these three linearly independent row vectors and take their transposes and stand them upright like this, they're still linearly independent. So this is a linearly independent set of vectors. So these are linearly independent vectors. And again, that's because they correspond to the row vectors of a matrix in row echelon form, the non-zero row vectors. Non-zero row vectors of a matrix in row echelon form are always linearly independent. So that's how we know these are linearly independent, and then when you take their transposes and put these guys down, they're still linearly independent. What have we got? We have found that these three vectors span V, right? The span of these three vectors is equal to V, and yet the three vectors are linearly independent. Therefore, this set of three vectors is a basis for V. And that is what we wanted to do, was find a basis for V. So we're done. Maybe I should point these arrows the other way and say, all right, so these guys are linearly independent. This set here with these three vectors, this is going to be a little tedious if let's just call this set, well, we can't say S because we've already got S. Let's call it B. Okay. So B is a basis for V. And that finishes it. Okay, I think I'm happy with that. So, this is just again, another illustration of how matrices are useful in linear algebra. Okay, so you got a bunch of vectors in R5, and you take the span of those vectors and thereby get a subspace of R5, and you want to find a basis for that subspace. And as you can see, the basis in this case ends up having just three vectors in it. So, as just an aside, or a kind of a spin-off from this, This means that the dimension of V is 3, right? Because a basis for V has been found and it has three vectors in it, so the dimension of V is actually 3. V was given as the span of S, where S has 4 vectors, but it turns out that S is not 4-dimensional at all, it's 3-dimensional. What this actually tells us, by the way, is that these 4 vectors can't actually be linearly independent. They're not. They can't possibly be. Because if they were, then these 4 vectors would be a basis for V, and you can't have one basis for V having 3 vectors in it and another basis for V having 4 vectors in it. We've already seen that any 2 bases for a finite dimensional vector space has to have the same number of vectors in it. Okay, so that actually tells us that these 4 vectors are not linearly independent without ever having to directly deal with figuring that out using the definition of linear independence.